can get started. So let's jump right in. So on Friday, we did all sorts of radicals using the rational exponents. But today is just strictly going to be square roots and non-perfect square roots. So a lot of times you can just use a factor tree to simplify radicals. Sometimes I do prefer to just break it down into a perfect square and a non-perfect square, and I'll show you what that means. So in this little blank after when the index is 2, what you can write is 2 of the same factor. Inside the radical, or I'm going to say inside the square root, appears once outside. Appears once outside the radical. What do I mean by that? I'll show you. All right, so let me zoom out. If you take something like the square root of 20, is that a perfect square? No, right? It's not a perfect square. There's not a whole number that I can multiply by itself twice to get 20. But what you can do is break it down into a perfect square and then a non-perfect square. I'll show you with the factor tree first, and then I'll show you how I like to do it to kind of speed it up a little bit. But on the side, let me just write 20. All right? You guys remember factor trees at all with breaking it down, things like that? Okay, so what are two numbers that multiply to 20?
2 and 10.
Okay, sure, 2 and 10. Can you break down 2 anymore? No, can you break down 10 anymore? 5 and 2, right? So now you're going to look in these fully broken down numbers right here, and you're trying to see which one shows up twice or multiple times. All right, which one is that? 2, right? So you see that 2 shows up twice, and then like I wrote in green, a number that shows up twice shows up once outside a radical. What number shows up not twice? 5, right? So that's going to stay underneath the radical. So 20, the square root of 20 is the same as 2 square root of 5. A lot of times the numbers can get a little big, and then maybe you don't think through the factors super efficiently, and then you end up with a whole bunch of numbers on your page. To avoid that, I find it a little bit easier just to remember your perfect squares. So the whole point is that you want to take something like 20 and then break it up into a perfect square times a non-perfect square. Is there a perfect square that's a factor of 20? 4, right? So 4, and we know 4 times 5 is 20. The square root of 4 we know is 2, and the square root of 5 cannot be broken down, so you can very simply just get 2 square root of 5 as your answer. That's a property of radicals similar to exponents. You can split up radicals if they're being multiplied. So if I have square root of 4 times 5, that's the same as the square root of 4 times the square root of 5. All right. Similarly, the reverse is true. So if I have something like the square root of 2 times the square root of 3, that's the same as if you did the square root of 2 times 3. So then you just get the square root of 6. Same exact thing with dividing. When you're dividing, you can either write it under the same square root, but sometimes if there's numbers out front, that might look a little bit tricky. So what I like to do instead is just simplify right away. Since this is the square root of 10 and the bottom is also under square root, you can just simplify 10 divided by 5. What does that get you? 2. So then you just get the square root of 2 as your answer. All right, let's say you had the opposite. Let's say you had the square root of 5 over the square root of 10. Where would that square root of 2 show up? On the bottom, right? So this would get you 1 over the square root of 2. And if you guys remember anything about radicals on the bottom, right, is there an issue with that? Yeah, right, so we can't have a radical on the bottom, so then what do we do to fix that?
Multiply the radicals for both sides.
Yeah. Good, right? So if you have a radical on the bottom, you multiply by the same exact number that you see on the bottom. on the top and the bottom, and then you get the square root of 2 over 2, right? So this, for our sake, is fully simplified, all right? So this, some people might leave it there. That is not fully simplified in this class. Okay, so let's do some of these examples. Let's start with the square root of 28. Again, you can do it one of two ways. You can either use a factor tree, or you can break it up into a perfect square and a non-perfect square. I prefer to do it that way, so I want you guys to also get used to it. It's going to speed up your work a little bit. How can we break down the square root of 28? Is there a perfect square times a non-perfect square that you can split it up into? You guys can just call it, 7 times 4. Right? So we know that 4 times 7 is the square root of 28. And then 4 is our perfect square, so I'm going to cross that out and I'm going to replace it with a whole number 2. 7 is not a perfect square, so I'm just going to keep it underneath the radical. 7 cannot break down anymore, so this is as simple as that number gets. All right, good with that, guys? Let me try the same exact thing with the next one. What about 48? Can we split this up into a perfect square and a non-perfect square?
6 and 8.
Those aren't perfect squares. I heard 4 and 12. Bless you. There's a better one than 4 and 12, but a lot of people would say 4 and 12, so let me do that. All right, what's our perfect square here?
4.
4, right? And then if you take the square root of 4, that's 2. We get 2 square root of 12. Right? So it did work. But is there anything we can do to 12 now? Can 12 break down anymore? Into what?
Into 2 and a 6. Or further.
4 and 3.
I would prefer the 4 and the 3, right? Because the 4 is the perfect square. So again, you would just have to keep going after that. So this would be 2 times, instead of the square root of 12, I can say the square root of 4 times 3. And the square root of 4 we know is 2. And the square root of 3 can't simplify. Just the only thing now is that you have a 2 and another 2. So what do you do with those 2's, do you think? Multiply, right? So this is the same as 4 square root of 3.
So if we were to give 2 times the square root of 12 like on a quiz, would that be like not fully simplified?
It wouldn't be fully simplified. You'd get some credit for
How do
doing
you
it,
know
breaking it down.
when it's fully simplified?
You always check the radical, right? So the radical, if you can break it down anymore, you should. And 12 is something that you can break down. It has a perfect square as a factor.
Okay.
But something like this, like how do you know this is done?
Oh, like you
Yeah.
have to check instead of
Because 3, you can't break down 3 anymore, so you just leave it alone. So some of you like the factor tree, so I'm going to show you the factor tree for this one again. So let's say you did 48 on the side. Maybe you did 6 and 8, right? With the factor tree, the only advantage to the factor tree is that this is fine because you would just have to keep breaking it down. How does 6 break down?
2 and 3.
2 and 3. How does 8 break down?
4, 4.
Okay, good. 2 and 4, 4 and 2. And then 4 can break down into 2 and 2. Now you count the pairs, right? So how many numbers show up in pairs?
2 and 9.
Okay, so there's a 2 and a 2, so that's once. There's a 2 and another 2, that shows up twice. And then this 3 is by itself, so that stays under the radical. So you get 2 times 2, so those are the whole numbers that you multiply, 4 square root of 3. Some people like that more. Sometimes when the number gets really big, though, it's a little bit time consuming. All right? But either way, you get the same answer. Are we okay with that? Good. So if you look at the next one, what's the only difference with this one and the one we just did? Good, there's a 2 in front, but we know what the square root of 48 is. What is it? Good, right? We just got that. 4 square root of 3. What do you guys think we do with that 2 in front? Multiply, right? So you just multiply whole number times the whole number. So this is going to be 8 square root of 3. Not bad? Okay. You can try the same exact thing with the next one. You guys can, again, either use the factor tree or find a perfect square. All right, again, I want to get you guys in the habit of using the perfect squares. Is there a perfect square that...
Yeah, 9.
Okay, good, right? So you guys see that? This is the same as 9 times 5. And 9 is, square root of 9 is what? 3, right? So this becomes, what? What does the square root of 45 become? like fully simplified?
3 times 3.
Good, right? 3 times the square root of 5. Nice. And then we have the 6 out front, so then this is what you multiply. Nice. So then you get 18 square root of 5. All right, not bad. Hopefully not too bad. Okay, guys, so let's do 5. What do we get for 5?
7 square.
Okay, nice, because 75, if you use the factor tree, you would break it down into what? 15 and 5 maybe, right? And then you can break down 15 a little more. If you use perfect squares, you can break this up already into 25 times 3. All right? And then 25 is a perfect square. And then you get 5 square root of 3, and then you have this 14 out front. 14 times 5 is going to get you 70. So you get 70 square root of 3. Not bad. All right, what do we get for 6? Nice, same exact thing here. 125 you can break up into 25 times 5. If you don't know that off the top of your head, maybe you need to practice your perfect squares a little bit. Why don't we do that now, actually? So we know 1, what's the next perfect square? 2 times 2? 4, what's the next one? 9, what's the next one? 4 times 4? 16, what's the next one? 25, what's the next one? 36, what's the next one? 49, what's the next one? What's the next one? And the next one? 100. Okay, so most people know 1 through 10. I would say try to memorize up to 15. Do we know 11 times 11? Okay, do we know 12 times 12? Do we know 13 times 13? Okay. What's the one after that? 14 times 14? My trick with this one is that if you know 169, the next one's just the reverse 196. And then do you know 15 times 15? 225. All right, so these are the perfect squares 1 through, whoa, hang on. What did I do? Okay, so these are the perfect squares 1 through 15. Why does it keep doing that? Okay. But anywho, right? Just some good things to memorize. So square root of 25 we know is 5. And then we get the square root of 5. We have this 10 on the outside. This should get you 10 times 5, 50. So we get 50 square root of 5. All right, good. What do we get for the next one? Okay, good, right? We know 600. This one should be an easy one. What perfect square goes in 600? 100, right? So we get 100 times 6. So we get 10 square root of 6. We can bring down the 5. This becomes 5 times 10 square root of 6. So 50 square root of 6. All right. Do we get an answer for 8? Wait, hold on. Yep, question.
Why don't you split the 6 more?
Okay, that's a good question. Some people don't know when to stop. Why don't you split up the 6 more? Let's say you did. What would you get? 2 times 3? Right? Can you break either of those down anymore? Does anything show up twice? No, so then even though it does have multiple factors, you can't, there's no perfect square inside of it, so you just leave it like this. So that's how you know when to stop, if you can't break it down into matching pairs or a perfect square times a non-perfect square. All right? Let's think about number 8. So again, our rule is that a whole number can only be multiplied by another whole number, a radical times a radical, right? So what are our whole numbers here? 5 and 2, so we can multiply those to get what? 10. What are our radicals here? 3, so we can do square root of 3 times the square root of 3, which is the square root of 9. What's the square root of 9? So we get 10 times 3, so 30. This one gets you a whole number. All right, are we okay with that one? That was the only one that was slightly different, but still shouldn't be too bad. All right, nice work, guys. Let's move right along. By that same logic, what can we do here? There's a couple approaches, but one approach is a little bit easier than the others. Okay, so you can do that, and then, what'd you say, Matthew?
I was going to say 2 5s, turn that into 4 5s, and then 3 on the outside. Or no,
Okay.
take that into
Okay, good. So the square root of 9, hopefully you guys can recognize that's a 3. I do agree with the 2 5s though, because we get the 2 square root of 5s is the square root of 25, which is just this, which is just 5. So we get 5 times 3, so 15. I find that a little bit easier than doing 5 times 9, which is 225. That's one of your perfect squares that hopefully we should have memorized soon, I would say. And then that does get you 15. But smaller numbers are easier to work with, so try to break it down as small as you can first. All right, what about the next one? Do we want to just do 11 times 44 and get a big number? Or is there something else we can do? Okay, good. We can break down the 44. How can we break that down? Good. 11 times 4. 4 is a perfect square, so what does the square root of 44 become? 2 square root of 11. Nice. And then we still have this square root of 11, so we're going to get square root of 11 times 2 square root of 11. And then these get you 121, which is just what? 11. So you get 2 times 11, so 22. What do you notice about radicals that are the same thing?
They like create like the number that's inside the radical.
Okay, yeah, good. So they give you the same exact number. So something like the square root of 2 times the square root of 2 is just going to get you 2. You could say it's a square root of 4 and then simplify it, but sometimes the numbers get big and you don't want to do that. All right, if you get like the square root of 10, you don't have to think too much about that. You know that's just 10. If you get a smiley face times the square root of a smiley face, what is that? Just a regular smiley face, no radical, right? Good. What about the next one? Okay, good. Which otherwise, if this was by itself, wouldn't really help us that much. But the 11 does help in this case because now I have an 11 times an 11. All right, you guys see that? So then what's the answer to this one? It's just 11 square root of 3. Nice. Not bad. All right, so far so good. What about these dividing ones? Our rule for dividing is the same as multiplying. So what we can do is divide radical times radical, or radical divided by radical, and we get the 7 and the 35. Can we simplify those into what and what?
1 and 5.
Good, right? So this becomes the square root of 1 over the square root of 5. What's the square root of 1? Just 1, right? So if you get a square root of 1, you don't have to write it because it's just 6 times 1, right? So then this becomes 6 over the square root of 5. And then good, we can't have that. So how do we fix it? Nice, guys. So then we get 6 square root of 5 over 5. Good at that one. See if you guys can figure out 13. Yeah, I like how you were doing it. So this is going to be what? The same as 16, and then this is 13. So 48 and 39 share a factor of 3. And you're allowed to do that, right? So this is the same as 5 square root of 16 over the square root of 13. Can we simplify any of those anymore? Yeah, good. 16 is the same as 4. So this is 5 times 4 over square root of 13, which gets us what? 20 over square root of 13. Can we simplify that anymore? Okay, good. We need a radical on the top and the bottom. So square root of 13, square root of 13. So then we end up with 20 square root of 13 over 13. All right, I'll leave that up. Okay, so 14, how do we interpret this? Like, what is this negative? Like, what should we do with that square root of 5? Good, distribute it. So that's going to go to each of these. What's the square root of 5 times the square root of 5? Just 5. Minus 2 times the square root of 5. There's nothing more we can do to that. You can't do a square root times a radical, so yeah, it's just going to be negative 2 square root of 5. And you can't do anything more. You can leave it alone. I know you guys like to make things maybe a little bit simpler than they need to be, but really there's no way to simplify that. One thing that you're going to hear me say a lot is you need to treat that radical like a variable. Could I do something like 5 minus 2x? Nothing more to that, right? Same thing here. This is 5 minus 2 and a radical. So they're not like terms in this case. But something like 17, what can we do there? Are they like radicals? Yeah, they're the same thing, right? So this is the same, similar as if you did 8x minus 6x. These are the same number. So this is just going to be what? 2 square root of 3. Good. Yeah, right? So you can think of it that way. Right? It's probably my fault. That's what I wrote on the board. But good, right? So you can just subtract the coefficients in front. You can treat them like terms. Could I do that? Let's say if it was 8 square root of 2 minus 6 square root of 3. What do you think? No, because these are not like radicals, right? You couldn't do, for example, 8x minus 6y. Can't really do anything more with that. So if you did get something like this, you would just have to leave it alone. All right. 15 and 16 are just more multiplying and dividing, so I'll skip those for now. All right, let's look at something like 18. You're still subtracting here, but looks a little bit different. Why? Good, right? The radicals aren't the same, so like you said, we would simplify the 24, right? Can we simplify square root of 24 or how? Okay, good. So we can make this, you said 2 2s and 1 6. So you can write that as 4 times 6. And then 4 is the same as 2 square root of 6. What do we do with that negative 2 on the outside? Good, multiply it. So this is negative 2 times 2. So negative 4 square root of 6. Minus 3 square root of 6. What does that get you? Very good. Just because these are like terms, or like radicals, let's say. All right, I'll have you guys try 19 and 20. Okay, did we know how to simplify the square root of 45? Okay, good. So this is the same as 9 times 5, and the square root of 9 is 3. So we get 3 times 3 square root of 5, which is just 9 square root of 5. And then how do we simplify this side? It's the square root of 36. That's just 6. So we get 7 times 6. So 42, so we just get plus 42. Can I do anything more with a radical and a whole number? Can't do anything more with a radical and a whole number. So you just leave it alone. Sometimes you get multiple terms in your final answer. That's perfectly fine. If they don't combine, don't force it. Same logic with this one, right? How did we simplify square root of 32? Into, what do you... Okay, 16 and 2. And the square root of 16 is 4, so we get 4 square root of 2 times 3. So we get 12 square root of 2. What about 63? How can we simplify that? Jot, what do you think? Okay. There's a better one with the perfect square. Good, 9 and 7. So this is 9 times 7. Or square root of 9 square root of 7, so then this gets you minus 4 times 3 square root of 7, so minus 12 square root of 7. Can we do anything more with that? Nothing more, because these are not like what? They're not like terms, or like radicals in this case. Again, it's okay if things have more than one term. That's fine. All right, these next two are good ones. Why do I say that? Just because there's a new operation. Well, not a new operation, but something a little bit new. In general, if it was just 2 terms times another 2 terms, how do you guys know to multiply those? Something like that, right? Let's say I had like x plus 1 times x minus 2. How do you multiply those? Foil it, right? something similar here, right? I have 2 terms times 2 terms. So you're going to FOIL it, right? 4 times 4 is going to get you 16. 4 times negative square root of 11 is minus 4 square root of 11. Square root of 11 times 4 is 4 square root of 11. And then square root of 11 times negative square root of 11, what does that get you? Good, negative 11. And then most times when we FOIL, we have like terms. Sometimes we don't, but this time we do. What are our like terms?
16, 11, and negative 4 times square root of 11 plus 4 times square root of 11.
Okay, good. So you could do the whole numbers. So 16 minus 11 gets you what? 5. And then negative 4 square root of 11 plus 4 square root of 11, what happens there? They cancel out. So your answer is just a whole number 5. That's always going to happen when they look like this, right? What do you guys notice about this one? About the 2 terms? What do you think?
It's the same thing, but there's just a plus and a minus.
Good, right? So any time that you have the exact same numbers with opposite signs, you're always just going to get the whole number. That's important for when we divide. And these are called, I'm going to write it on this side, conjugate pairs. So there's your vocab for today, right? These are conjugate pairs. Right? And again, conjugate pairs, when I say that, I just mean these are the same numbers, they just have opposite signs in between. All right. I'm going to leave that on the board, but while I do that, let's think about 22. All right, what does it mean to have something squared?
You get like a normal number. And that's like square root.
Okay, so when you're squaring something, you're multiplying by itself twice, right? Some people, what they do is they see this 2 and they distribute it. Were any of you thinking that? You can be honest, that's fine, right? Because that's not what you do. But it is a common mistake, right? You don't want to do that. Just because there is now a minus in between. If these were just factors, like if it was 3 square root of 7 times the square root of 3, you could do that. But since there is a minus in between, you can't just distribute the square. But instead, what you would do if something is squared is you would write it twice. Right? Because that's what squaring something is. You write it twice and multiply. So we get something like this, and then you end up foiling it. Good. So 3 square root of 7 times 3 square root of 7 is what? When you multiply?
42.
Okay, it's going to get you 3 times 3, so 9. Square root of 7 and square root of 7 gets you what? 7, and so this whole thing is going to get you 63. Good. And then now let's do 3 square root of 7 times negative square root of 3. All right, so these you need to be very careful, guys. This is where a lot of people make a lot of little mistakes. What multiplies here when you do this term times this term? Good, the inside. So 3 square root of 7 times square root of 3 is just going to be minus 3 square root of 21. We're going to do 7 times 3, right? They're both under the radical. Inner times the inner, same exact thing there, right? What is that going to get you? Good, it's another negative 3 minus square root of 21. Again, we're going to do this radical times this radical. And then when you do last times the last, negative square root of 3 times negative square root of 3, what does that get you? Good, right? Plus 3. So square root of 9, 3. Yeah, good. And then now you can combine like terms, right? 63 plus 3 is going to get you 66. And then these are also like radicals. These are going to get you negative 6 square root of 21. When they're like radicals, you can just combine the numbers in front.
And that's it.
Nothing more you can do there, so you leave it alone. Okay, when you're dividing radicals, you cannot have a radical in the bottom. So we want to eliminate it, and this is through a process called rationalizing the denominator. The denominator. All right, so something like 5 over the square root of 2. I'm not going to waste too much time on that because we've done a couple of those already. But something like this one, 2 over 2 plus the square root of 3. The difference here is that now there's a whole number plus a radical. So we can't just multiply by the square root of 3, let's say. But a couple examples ago, we just multiplied 2 radicals to get a whole number that kind of looked something like this. Do you guys remember that vocab word that I just talked about? What was that? What was it called?
Conjugate.
Okay, good, right? So we need conjugate pairs here to get rid of that radical in the bottom. So for something like this, what would the conjugate of 2 plus the square root of 3 be? 2 minus the square root of 3. Which one? Like that 2?
Yeah, you have to get rid of that one also.
That comes as a result of getting rid of that 3, right? We can't get rid of that 3 without also getting rid of that 2. At least in problems like this. But what you do to the bottom, you have to do to the top. So we're going to do 2 minus the square root of 3 on top as well. I'll do the top first. When you distribute that, we end up with 4 minus 2 square root of 3. And on the bottom, we know that this is going to get us a whole number. If you FOIL it out, the radicals are going to cancel. Your shortcut here is if you have a plus b times a minus b, that's just going to get you a squared minus b squared. All right, so that's kind of the technical notation for it. But let's apply it to this problem. What's the square of the first number in these parentheses? When you square it, right, it's going to get you 4 minus what's the square of the second number in these parentheses? What's the square root of 3 squared? It's just 3, right? So there's your shortcut to foiling it. If you didn't know how to do that, then you can just FOIL it as normal. There's no big deal with doing that. All right? But then you just simplify what's 4 minus 3. Minus is just going to be 1. Yeah, good. So then this is going to get you 4 minus 2 square root of 3 over 1, which anything over 1 is itself. So then this would be your final answer. All right. So you just have to be a little bit careful with these. All right, I don't want to waste any more of your time, so I'm just going to skip to number 25. This is similar to what we just did, right? So let's think about this one. This is not simplified because of the radical in the bottom. So how do we get rid of that? What are we going to multiply it by? The conjugate pair, right? So this is going to be 3 what? Minus the square root of 2. And I'm going to do that to the top as well. Get out of the way. The top, what does the top become after you distribute the 1? It's just the same thing. So it's 3 minus the square root of 2. What does the bottom become after doing your shortcut? What's that first number squared? 9. Minus, what's the second number squared? 2, right? And what's 9 minus 2?
7.
So we get 3 minus the square root of 2 over 7. And we get that as our final answer. And that's perfectly fine the way it is because there's no more radical on the bottom. All right, we'll do the same exact thing with the next one. All right, first, any questions on anything so far? Okay, good. I'll walk you through the next one as well. Again, same exact process. What do we multiply this one by? Okay, so the bottom's the issue, right? It's 1 minus the square root of 2. It's going to be 1 plus the square root of 2. Good, 1 plus the square root of 2. I'll let you guys do the shortcut. If you don't know the shortcut, that's fine. Just FOIL it. You should get a radical cancel out.
You can do for the top two, right? So make it like 3.
The top you can FOIL, yeah. But let's work on the bottom, right? What's the first number squared? 1 minus what's the second number squared?
Square root of 2.
Okay, it's 2. All right. And now let's FOIL the top. 3 times 1 is going to get you 3. 3 times the square root of 2 is plus 3 square root of 2. Inner times the inner is going to be plus the square root of 2. And then last times the last is going to be just 2. And then now what we can do is simplify as much as we can. What are our like terms on top? Okay, good. So that's going to get you 3 plus 2 is 5. And then 3 square root of 2 plus the square root of 2 is what? 4 square root of 2, right? We pretend that there's a what in front of this radical? A 1, right? And you combine the numbers in front. Over, what does the bottom become? -1. I think we do let you guys just leave it like this. I personally don't like how it looks like this. Does anyone see why? Then -1, what does dividing by -1 do? Yeah, it makes the whole thing negative. So what you can do instead of leaving it like this is changing all of the signs on the top. So then this becomes what? Yeah. I like this a little bit more. I do believe for our sake you can leave it like that. I'll just have to make them equally correct, so you don't have to worry too much about that. All right, but that's it for this lesson. I know it was a lot, but